Imagine a runway in Arizona. The airport elevation is 5,000 feet, but the temperature has climbed to 38 degrees Celsius. As a pilot pushes the throttle forward, the aircraft feels sluggish. It uses nearly the entire runway, finally lifting off and clearing the trees by a narrow margin. The pilot survived, but they had ignored a critical atmospheric shift that occurs on every hot day. This is density altitude, the altitude your aircraft aerodynamically performs as if it is at. High density altitude means there are fewer molecules in the air. With less air to work with, your wings produce less lift, and your propeller generates less thrust. To find this number, we start with pressure altitude. This is the altitude indicated on your altimeter when you dial the setting to the standard pressure of 29.92 inches of mercury. We then compare the actual temperature to the International Standard Atmosphere, or ISA. Standard temperature starts at 15 degrees Celsius at sea level and decreases by 2 degrees for every 1,000 feet of altitude. Based on that rule, let's look at our 5,000-foot airport at 38 degrees Celsius. Do you think the density altitude is higher or lower than the 5,000 feet shown on the map? Write your guess in the comments before we run the numbers. High-density altitude creates an invisible disconnect between the elevation printed on the map and your aircraft's actual capability. Because you cannot see the air thinning, mathematical calculation is the only reliable way to guarantee a safe departure. To solve the Arizona scenario, we use the standard formula. Density altitude equals pressure altitude plus 120 times the ISA temperature deviation. We start with our pressure altitude of 5,000 feet. Next, we find the standard ISA temperature for that height. Starting at 15 degrees at sea level and subtracting 2 degrees for every 1,000 feet means the standard temperature at 5,000 feet is 5 degrees Celsius. This next step is where errors often occur. To find the ISA deviation, you must subtract the standard temperature from the actual temperature. 38 minus 5 gives us a positive deviation of 33 degrees. Now we complete the math. 120 times 33 is 3,960. When we add that to our pressure altitude of 5,000, we find a density altitude of approximately 8,960 feet, roughly 9,000. The Arizona pilot wasn't flying in a 5,000-foot environment. Aerodynamically, their engine and wings were fighting a 9,000-foot atmosphere. This 4,000-foot difference explains why the aircraft struggled to leave the ground. At a density altitude of 9,000 feet, the penalties are measurable. The takeoff roll increases significantly because the engine produces less power and the wings require more speed to generate lift. Once airborne, the rate of climb is severely degraded. In MACE conditions, your best rate of climb, Vy, decreases, while your best angle of climb, Vx, increases slightly. Humidity makes this worse. Because water vapor molecules are lighter than the nitrogen and oxygen they displace, humid air is less dense, pushing the density altitude even higher. A specific question on the FAA written exam tests your understanding of a counterintuitive variable. Does your indicated stall speed increase when the air is this thin? It does not. An aircraft stalls at the same angle of attack and dynamic pressure, regardless of the density. While your true airspeed, your actual speed through the air, is much higher at 9,000 feet, your indicated stall speed on the dial remains exactly the same. Recognizing that density altitude degrades every performance metric except indicated stall speed allows you to navigate the most difficult sections of the written exam and maintains your situational awareness in the cockpit. Screenshot this summary for your records. It contains the core formula, the standard temperature lapse rate, and the performance rules you'll need for both your exams and your pre-flight planning. To recap the principles, high density altitude degrades aircraft performance. High humidity makes that performance even worse. However, your indicated stall speed remains constant regardless of the air density. Before you head to the flight line, share your observations in the comments. Have you ever noticed a significant difference in your takeoff roll or climb rate during a particularly hot summer day? Memorizing these calculations is not just an academic exercise. It provides the framework required to respect the atmosphere and ensure you never ask your aircraft for performance it cannot physically deliver.